Okay, let's see. From yesterday's lesson set, I said I would introduce the topic changing the limits of integration. So let's do it. I said we do it with a simpler problem. So what's the simpler problem? I think the exact one you did yesterday. So we're going to integrate from 1, let's see, from 2 to 5. I'm trying to remember yesterday's problem. Square root of x minus 1 dx. All right, which is the same thing as 2 to 5. Lost my train of thought already. Oh yeah, x minus 1 to the 1/2 dx. All right, that's easier to integrate from that perspective. So we have x minus 1 to the add 1, 3/2, dividing by 3/2 gets us 2/3, and we are now here from 2 to 5. Substituting in 5 gets us 2/3, 4 to the 3/2 minus 2/3, 1 to the 3/2. And we did that out, square root of 4, 2, 8, 16/3, 16/3 minus 2/3. And that's the problem you did yesterday. And I hope that that makes a little more sense to you today than it did yesterday, because you did it again. Now, what could we do? We could change x minus 1 to the letter u. And we could say, well, let's do that from 2 to 5, but let's do this one over here from 1 to 4. Okay? If I have the square root, remember this is going to fit inside a square root, so I really have the square root of x, really, and I'm going to go from 1 to 4, and I'm going to look at that area. Well, is that the same thing as the square root of x from 2 to 5? Should be. If I draw it, well, all right, so let's do the integration using u substitution. So I'm going to let u represent x minus 1, so I don't even think I have to write that. I think I can do the square root of u du, but u, 5 minus 1 gives me an upper limit of 4 and a lower limit of 1. Well, remember, that's to the 1/2. So now we're at 2/3 u to the 1 to 4, 3/2, right? And I'm right back there immediately. So that's going to be 2/3, 4 to the 3/2, F, big F of B minus big F of A, 2/3, 1 to the 3/2. Right, and that's changing the limits of integration. We'll start doing those in the lesson set. And if you don't change the limits and you use u substitution, well, you don't have the same picture of area. All right, now here's another problem that you did yesterday. Let's see if you can have at it. Let's do x cubed plus 2x. So let's let f of x equal x cubed plus 2x. And g is the inverse of f. And I want to find g prime of, let's find something that's nice and friendly. 125 and 10, 135. All right, so what did we talk about yesterday? Well, we looked at x squared and the square root of x and the reciprocal relationship between derivatives. So, I think I can see what f of 5 gets me. F of 5 gets me 135. And I think I can find f prime, 3x squared plus 2, and I think I can drop a 5 in there. And if I do, then f prime of 5 is equal to 77. So what's the inverse? The inverse is g of 135 gets me 5, and therefore g prime at 135 is equal to 1 over 77. That's your answer. Now, once again, what is a derivative? It's really a calculation, y2 minus y1 over x2 minus x1. And yesterday we said, what do you do when you algebra 1 through your algebraic career? To find inverses, you switch the x's and the y's. And if I switch the x's and the y's, then this is x2 minus x1 over y2 minus y1. And I do believe that when you take a number and you flip it, you have a reciprocal. Okay, day 2 of hearing that. I like people to hear it 4 times and not only hear it 4 times, but then do a new problem like it 4 times. And you're not quite getting that practice, but you're getting quite a bit. All right, so save that. Yeah, I'll need this space for work. All right, so here we have a picture. We've got a curve. Big F of x is defined to be 1 to x gt dt. This is the graph of g. Let's do the fundamental theorem. Little g, big F of x, is the same thing as little g becomes big G of what? Drop in the x, drop in the 1. And we want to make a connection here. We want to know what f of x is because we're probably going to be talking about what's this function doing, and a derivative helps us. And that's g of x minus 0. Ah, this is the graph of the derivative of that. Maybe we can answer some questions now. How about big F of 4? I hope you know what that asks you to do. It asks you to do this, which is accumulate area from 1 over to 4. And if you do, this is an x value of 1, which means the width is 2. The altitude's -4. That's -8, and it's a triangle. So I now know that big F of 3 is equal to -4. But I got to go all the way over here to 4. That's a width of 1, a height of 2, so I'm adding 1 unit there. So big F of 4 is adding 1 unit to that, so I think that's -3. All right, how about big F of -4? Well, now I'm looking in the other direction. If I'm looking in the other direction, then I don't have a positive width anymore. So from 1 to -1, I'm going back 2 and still going down 4. So instead of accumulating -4, a negative times a negative is a positive 4. So I now know that big F of -1 is equal to positive 4. Right? Because I do believe we've talked about if x was 1. If x was 1, so big F of 1 appears to be 0, not accumulating any area, not slicing those bread, not putting them together. Now, I've got to get to -4, so I've got to get over to here. That's a height of 6. That's a width of 3. 3 times -3. I'm moving in this direction. -3, looking up. -3 times 6 is -18. Cut in half is -9. So if I subtract 9 units from where I was before, did I write that one down? F of -1, yeah. So if I add 9 units to the number -9 to 4, then F of -4 is equal to -5. If I didn't make a careless error, that should all be true. Let's clean this up. And let's talk about some of the characteristics of little g, which happens to be the same as little f. When is big F going up? Big F is going up when its derivative values are positive. And these are all derivative values. In other words, little f, big F is going up at 6 to 1 at -4. So at -4, I'm going up at 6 to 1. At a number in between, I'm going up at 3 to 1. I'm flat right there. I might as well sketch it right now. I'm flat. 0 slope. Then I'm at something probably akin to -2. So I'm going down at 2 to 1. Then I'm going down at 4 to 1. Then I'm going back down at 2 to 1. That's a change of concavity, folks. And then I'm flat again. And then I'm going up a little bit at 2 to 1. So those are my endpoints. So f of -4 is -5, and f of 4 is -3, so this is a little bit lower. than that. So this is the coordinate 4, -5. The point of inflection occurred at 1. Oh, what happened at 1? My derivative, first derivative, is decreasing, then increasing. That's why I have concave down till I get to 1, and 1 gets me a 0, by the way. And I'm going down at 4 to 1 right here. That's the fastest I'm going down. And if you want to look at cubics in the, not that this is a cubic, but if you want to look at first point of inflection we generally encounter is with the cubic, go to the playlist and look at some of the geometric implications as to why. All right, so then this was big F of 4, which is -3. So this was 4, -3, and I'm going up at 2 to 1 right there. All right, so when am I increasing? Looks like I'm increasing to here, where it gets to be flat. So all of this translate into telling me that these are slope values. They're positive, so this critter's going up until I get to that value. And then it's going up again over here from 3 to 4. So this is 3, and 3 got us -4. A little bit lower than -3. Right, so I can start to put in some values. Concave up from 1 to 4. What's happening in this graph from 1 to 4? It's increasing. So if you think of this as a velocity graph and your speeds are increasing, boom. All right, so let's go to the other page. Well, you don't have that worksheet in your hand, but here's some more practice. And hopefully it's going to be fairly quick practice because we've done these problems. Use a limit to express the rate of change of x cubed at x equals 5. We've done this problem. So now it's a question of, are you recalling it? And if you are, you're putting something in your longer term memory. So there's two ways to do it. One is to work with h going to 0 and taking 5 plus h cubed minus 5 cubed over h. In other words, if we were looking at square cubing, and I took 5 and I cube it, I get 125, which shows up there. And if I did 5 plus h, and h goes to 0, so 5 plus 0.001, and I cube that, I would get 125. Let's see, I got to get 9 zeros here, so it's going to be 0, 1, 0, 0, 1, 5, 0, 0, 1, I believe. Okay. And I think we're beginning to see a very small change. That's 3x squared, excuse me. What was I doing? 3x squared, so it's going to be 7.5 here. And then it's 3 times 5. That looks right. That looks good to me. So this is your h. And so if I call this 5 plus h, then what's x2 minus x1? Just h. And so we're looking at that microscopic, what's going on here? Small change in x, replicating a dx here. Okay, so that's one way to express the rate of change of the cubic at 5. That's a crazy board. Now, if we let x go to 5, then we're really looking at x cubed minus 5 cubed over x minus 5. I'll change that to 125. And that's exactly what we were doing here at 5.001, getting us 125.075. So that's 3x squared, right? And 5 getting us 125. Can you see the y2 minus the y1 over the x2 minus the x1? So this answer actually is 75. And it doesn't hurt to see the factored form for a difference of 2 cubes again. You're working with cube roots. You're taking the first cube root, squaring it to get back to x to the 3. That's going to disappear by bringing in 5x, and minus 5 squared is 25. And what happens when you put 5 in here? You get 25, you get 25, you get 25. There's your 3 squared, there's your magic box, right? A layer, a volume. Well, that's a derivative, and you're looking at the 3 squares. We've talked about that in previous lesson sets. All right. But I think repetitively hearing this stuff will have a positive impact on you, on your foundation. Because if you can connect things to a picture, you're flying high. All right, average rate for x to the 2/3, which is a graph that fits in between y equals x and y equals x squared. Kind of looks like this. Okay, on the right-hand side, so we got x to the 2/3. We're going to go from 1 to 8. So 8, cube root of 8, 2, so that's a 4, that's a 1. So the average rate of change from 1 to 8, it's hard to draw that, is 3 to 7. Okay, the magic value C. Yeah, I'm hoping that we've said that enough that maybe you're starting to say, oh, he's doing the mean value theorem for derivatives. So there has to be some place in that interval, some x value, where I'm going up at the same rate as the average rate. So we set the derivative 2/3 x to the minus 1/3 is the same thing as the cube root of x in the denominator, to 3/7. Okay, so division on the multiplication by 2 on the right is division on the left. So that's 14. This is 1 over that. I'll take a reciprocal right now. So 3 times the cube root of x equals 14 over 3. Okay, so multiplication by 3 becomes division by 3. And division by 3 makes that a 9. And now cube rooting means I've got a cube on the other side. And that's a number between 1 and 2. And if I cube it, I'm somewhere between 1 and 8. Ah, isn't that nice? Sure I didn't say that properly. Maybe I did or didn't. Not sure. All right, but that's the process. You always want to check that your answer is in the interval. Average value of that function. Just the calculation. Can you just write the average value of this function from 1 to 8? It's actually a nice picture. So let's go back to that picture. So from 1 to 8, what I'm really doing is looking at this area and redrawing it as a rectangle, and that seems to me to be the altitude, which is a y, expressed as f of x. I want to make sure you know when you see f of x, you're talking about a y value. Okay? But we are going to find that y value by doing what? Getting the area under the curve. Well, that's simply 1 to 8, x to the 2/3 dx. Right? And I have to take that area and I have to divide it by the width. And that's going to give me that average height. I can't think of a situation. Maybe average rainfall. Maybe that's how you... Anyway, compute that. Who knows? F of x. Little f of x. Just the calculation, so that one's done. Little f of x is x squared, x minus 3x plus 8. And we want to know when big F is increasing. Well, we talked about that 10 minutes ago. Big F is increasing when its derivative, first derivative, is positive. So we want to be able to graph this quickly. X squared, no change sign. 3, linear change. Negative 8, linear change. Putting a big number in gets a big number out. Big number in, big number out. Linear change. Linear change. When am I positive? From negative infinity to negative 8, 3 to infinity. Negative infinity, negative 8, you can't bound. Negative infinity, union, 3 to infinity. That is when big F is increasing. Okay, new problem. New F. So we're going to look at a new function whose notation derivative of little f, oh, little f is the first derivative. I think that represents the second derivative. So the second derivative is a parabola with roots at -2 and 5. Looks like the second derivative is positive, then negative, then positive. Looks like I have points of inflection. Big F has points of inflection at -2, 5. Because when the second derivative is positive, I'm on a concave up interval, then a concave down interval, and then a concave up again. And I want a concave down. So for x values less than 5, but bigger than -2, big F, concave down. Now, if you wanted to integrate this to get little f, and then integrate again to get big F, little f is an x squared, so derivative of little f is an x squared, so the next one would be an x cubed, and so we would have an x to the 4th type problem. We have 2 inflection points, so an x to the 4th, there's 1 inflection, there's 2 inflections, right? Just giving you an example. I don't know what big F looks like. We'd have to do more analysis. Get some space here, the final frontier. Oh no, that's the Starship Enterprise. Sorry, I digress. All right, so let's actually do this integral out. Oh no, we're making an integral. All right, that's the one we're going to do that integral on. So let's bring this board down a little bit, and I'll actually work right here. All right, so I need to know something about this function. And I know what I get from that function if I put a 1 in. 1 minus 4 minus 3 plus 5, I get a 2. Ah, what happens if I put a 1 here, an x here, and a 2 here? Then I have an integral that accumulates area under some curve. And what happens if I go from 1 to 1? No area accumulates, but I get a 2. Oh, I picked an x equals 1. I got a 2. So I need a starting place. And then the question is, under what curve? Well, that's where I need the rate of change function. So I need 3x squared minus 4. And that gets me the height of millions and billions of rectangles, but I need some width or I don't have any area accumulation. So I need another dimension. So I'm getting this determines what the height is, and that height is determined by that x value, and that is the width from x2 to x1, one of those 5.01 to 5 kind of subtraction thought process. Awkward. Okay? Second or third day you've heard that. Patience, reflection. Let's do this one out. So let's integrate 4t minus 3, which becomes 2t squared minus 3t. Let's go from 2 to x, and then let's add 5. So that looks like it's going to be, I'm going to do it this way, and then you can clean it up later. So this is 2x squared minus 3x, and this is 8 minus 6. You can clean that up. Well, it's not hard. Minus 2 plus 5, 3. And a 2 gets us a 5, yes? From 2 to 2 would get us a 5. Well, let's put a 2 in it. 8 minus 6 plus 3. 2 plus 3 gets us 5. Oh, that's nice. I like that. All right. Local max for minus x cubed plus 12x. That is actually in graphing form. So we're going through the origin at, was it positive 12? Oh, we're going up through the origin at positive 12, right? But it's a negative cubic. So we're going to get something that looks like that. Local max is on this side. Be helpful if I put the problem in front of you. So we're looking at this function, okay, which is the same thing as minus 1 times x minus 0 cubed plus 12 times x minus 0 That's the graphing form for a cubic. If you want to learn how to do that, go to the cubic playlist. So 0 plus minus the opposite of positive 12, negative 12 over 3 times a. This is going to give me the x values of local max and mins. And I know I am on this side, so I know 2 is going to get me minus 8 plus 24. Notice the 3-to-1 ratio. 3-to-1, but no, sorry, it's a coincidence here. So minus 8 plus, a little mix up here with the bx squared term, which isn't there. All right, so minus 8 plus 24, positive 16. That's our local max. Now, proving it, we need to do it with calculus now. So y prime minus 3x squared plus 12. We set that to 0 because that's a slope of 0 right there. And I hope you can see that x squared equals minus 12 over 3, negative 3. So therefore x is equal to the square root plus minus of that. Right? And we want the positive. Why do we want the positive? Because y double prime is equal to minus 6x. Minus 6x is the second derivative. And at 2, the second derivative is negative. And when the second derivative is negative, we have a concave down situation with a slope of 0, proving that 2 gets us our local max of 16. Bigger numbers than 16 over here on the left side. I hope you can notice that. All right, that's the conversation you wanted to have. Now, let's look at this. Minus 3x squared plus 12. That's a parabola with a vertex at 0, 12. Okay? And if this is slopes, then that's my biggest slope is 12. Now, where are you going up fastest as you look at this? I hope you say right there. That's where the tangent to the curve is biggest negative. That's where the biggest negative is. Biggest positive, excuse me. That's where your biggest positive slope is. No coincidence that it occurs at the vertex of this parabola. Okay. Now, what else do I have? Sine x plus y equals 3x. I'll do the problems here. I can do this now. I can get rid of this and then work above it. Save a little time, perhaps. Not having to recopy. That's the one we just did. All right, so we want y prime. So I got to do the cosine of x plus y times 1 plus y prime equals 3. Everything that has an x has a dx. Everything that has a y has a dy. And when I divide by dx, the dy over dx does not cancel. All right, so this is going to be 3 divided by this cosine of x plus y minus 1, and that's y prime. All right, so to find the slopes of that curve, I got to use an x and a y value. All right, dy dx, that's what we were looking for, and we just found it. Okay, so now we have a differential equation. You do enough of these, you'll know that I believe, is going to become 3e to the 5x squared over 2. I think that's going to be our answer. So we change y prime to dy over dx so that we can see the separation of variables more easily. 5x stays on this side, but I bring the dx over. Y minus 7 goes to this side. And that's going to be with a dy and a 1. I hope you can see that that becomes the ln, the absolute value, but I'm just staying on the positive side here. So let's go y minus 7 equals 5x squared over 2 plus c. So y minus 7 equals e to the 5x squared over 2 plus c. I hope you've seen that enough with the earlier lesson sets that you recognize that as ae to the 5x squared over 2. When you put a 0 in now, either the 0 is 1, so I need to get my 7 on the other side. and a 0 got me 10, so e to the 0 is 1, and I got to get to 10, so that's there. Not sure I wrote that plus 7. I forget now if I remember to write the plus 7. I know I had the 3, okay, but not a lot of sleep last night, and it probably shows. But I do want to get you to a daily practice, so I'm kind of pushing through this. Bounded area, we're going to do it in terms of x and y. Y equals x squared. There we have y equals x squared. Y equals 9. I think we have some area here. Right, now that's a y equals 9, and that's an x squared. I wonder what this distance is. I guess it depends, these distances depend upon where I am on the x-axis. But I think I'm measuring 9 minus x squared. And I think I'm doing it from -3 to +3. Now I got to give these little strips of height some area, so therefore I need a width to those altitudes, because every one of these altitudes, every one of those, is going to be 9 minus x squared. Yeah, when x is 0, this is 0, and this is 9, that's 9 units long. When x is 1, y is 1. 9 minus 1 is 8 units of area, 8 units of height. Now let's do it in terms of, y. But I'm going to do something, I'm just going to double this. So I know from here I'm going from 0 to 9, so that changes this. And that x value here, there is none, there's no change there, so that's still a 0. I'm going to double this because I got another side over here, so I'm just going to double y equals x squared, then I guess x equals plus or minus the square root of y. So I'm going to call this the square root of y. And I probably should have done both of those out to show you that they should be the same thing. We've done that enough. That's 2/3 y to the 3/2. We just did that earlier. 0 to 9. Square root of 9, 3, 27, 54 thirds times 2, 108 over 3. And I forget what the other one was. It wasn't hard to do. It was 9 minus x squared from a to b, -3 to 3. Why don't we double this one? Why don't we double this one? So therefore we go from 0 to 3. Let's get that at dx. So that's 9x minus x cubed over 3. We're going to double this from 0 to 3. 3 cubed, 27 over 3. That's 27 minus 27 over 3. So that's, what's the quickest way to do this? I know there's a shortcut here, but I'm not spotting it. So 81 minus 27 over 3 is 61 minus 7, 54 over 3. And if you double 54 over 3, lo and behold, you get 108 over 3. It was probably worth the time to do that. All right. Trying to keep the videos so that they're not terribly long. All right, so let me make another problem up and you can try it. And I just want to not have to pause and do it again tomorrow. So let's look at dy dx equals, how about we look at x squared, y minus 4. 0 gets you 20. Okay, so if that's true, then I should have 16e to the x cubed, where am I? X cubed over 3 plus 4. So do that out and you should get that answer. And what I'm suggesting, and the reason I'm doing this, is can you see a shortcut? Whenever you're doing a problem, instead of, when you're done, take a moment. Connect the original problem to the answer. The original problem to the answer, and a lot of insights can accrue, and a lot of shortcuts as well. All right, dy over dx equals 2xy, and 0 gets you 10. dy over dx equals 2x over y. And if you want to access more practice, there's tons of these on the internet. This is called separation of variables. So you put a little query into Google and say, hey, give me some problems that deal with calculus separation of variables, first order. All right, so move your variables, get them together, 2x dx. We're going to have y squared over 2 equals x squared plus c. Throw your 0 in right now and get 10. Okay, so 0, 10, throw in 0 and 10. We've done this problem before. That's 50. Doesn't hurt to do the same problems over. So therefore, I now have y squared minus 2x minus x squared equals 100. Okay, I got a hyperbola, and probably don't work with those much anymore. I'm trying to get up to grade level, and so this is disappearing from curriculum. But let's move on. Big F of x. I think we can do it here. Almost done. Big F of x. Let's just move the camera. There we go. Good enough. Big F of x from 4x to x squared t squared dt. What's the little f? Do you know the shortcut? Do you know the shortcut? I hope so. We take x squared, we drop it in, that gets us x to the 4th, times the derivative of what we dropped in is 2x. Drop 4x in and square it. You're going to get minus 16x squared and times 4. It might be worthwhile to do this out. I know that it's getting long, but t cubed, t squared becomes t cubed over 3, and we are going from x squared to 4x. So if I did that, I would have x to the 6th over 3 minus 4 cubed, 64 x cubed over 3. Well, I've got to pause here, so I'm going to do this problem first thing on the next. I literally didn't have a lot of sleep last night. So, brain is really at the end of videos. I start to have skips. So I'll do it tomorrow. Bothers me. I should do it now. X squared, x to the 3 over 3. All right, x to the 3 over 3, and I'm dropping x squared in. Okay, that's x squared to the 3rd. That's x to the 6th over 3. So that derivative becomes 6. Maybe I'm just not doing this out here. 6x to the 5th over 3. Dropping it down once. That's 2x to the 5th. That's what I have here, 2x to the 5th. Okay, so this is just brain slowing down. All right, you got some practice. That's the main thing. Okay, have a good day.